Hello students, welcome back to CLARI Concepts, Unleashing the Conceptual Learning, which is what we are doing so. And if you want to have more lectures on this, you can refer our website called clariconcepts.com. So today in this lecture, we are going to solve several numericals of Newton's law of viscosity, which we have already understood. So if any of you have not referred my lecture on Newton's law of viscosity, I kindly request you to go through that lecture first and then come back to this numerical portion, because unless and until you understand the theoretical aspects of this law, you are unable to solve the numericals. So let us move ahead with the first example that we have. Two infinite parallel plates are separated by a distance of 3 mm. and the water is filled between the plates having dynamic viscosity equal to 1 centipoise. Now see, before I move on to the numerical, I would like to say you several suggestions or other several inputs for you to solve numericals. In engineering, all the numericals are referring to the real life systems. They are not the hypothetical situations given to you. So I request you to try to understand numerical and try to imagine the system given to you and try to feel the values that you get at the end of the day. Right, the numerical values. See why I am saying this. One of the student of my class, when we talk about diameters, he said the diameter of the shaft is coming out to be, sir, 8,000 meters. Now 8,000 meters is almost 8 kilometers. Without even understanding the value that he or she has received in a numerical, without understanding the practical aspect of it, they come to me and say that, sir, this is the answer. I would say to all the students that please do not grow with a vision that whatever numerical is given to you, will get some random numbers. All this number represents something in engineering domain. So 8,000 meter diameter of shaft, which is 8 kilometer of diameter. You know what is 8 kilometer distance? And that much diameter of shaft is huge, where you will find bearings and all the other stuffs to mount that, right? So whenever numericals are given to you, think about it as a practical situation given to you to solve it, right? Okay. So I have been given two infinite parallel plates which are separated by a distance of 3 meters. So I have two plates and the distance between these two plates is 3 mm, right? 3 mm. And the water is filled between the plates having dynamic viscosity equals to 1 centipoise. So I have water in between these two and the viscosity is 1 centipoise. The upper plate moves at the velocity of 2 meters per second and the lower plate is stationary. So I can say this lower plate is stationary, fixed, and the upper plate moves with a velocity of 2 meters per second. Assuming linear velocity profile, determine the shear stress on the fluid layer at a distance of 1 mm from the bottom plate. What does it mean? It is said that assuming linear velocity profile means what? From the top point to the bottom point, we know that the fluid layer which is at the topmost portion has the same velocity as the upper plate, and the fluid layer which is lying at the bottommost portion has zero velocity because the bottom plate is fixed. So in this case, we know that all the intermediate fluid layer will have intermediate velocities. So here they said that the velocity distribution is linear. Assume that and find out the stress, shear stress at the fluid layer at a distance of 1 mm. So what you need to find? That if you talk about the distance of 1 mm from the bottom plate, you have this fluid layer. So they are asking that if you cut this fluid layer, you will see the shear stress developed somewhere over here is like this. So you need to find the value of shear stress on this layer. Got the point? Let us move ahead. So given data, what is given to me? I will just write all the values. First value given to me is the distance between the plates is 3 mm. So the length L is 3 mm. Now always I would request another suggestion to all of you that whenever any data is given to you, you try to convert all this data in SI unit before you put all those values in the equations. Okay, always keep this habit. So if I want to convert 3 mm into meters, I will divide the value by 1000. So this is 3 by 1000, that means 0.003 meters. Now, then I have been given the viscosity of water as 1 centipoise. Now viscosity over here is given in poise, that means they are talking about the dynamic viscosity, mu. So mu is given as 1 centipoise. So mu is, what is 1 centi? It is 10 to the power minus 2. So I could say this is 0.01 poise. And again, poise is not the SI unit of this particular variable. So if I want to convert poise into the SI unit, so SI unit of mu is Pascal second, and we know the conversion factor is 10, right? So I will divide this value by 10 to get the SI unit, that is Pascal second. So mu actually will be 0.001 Pascal second. Now this value I will use in the equations, right? Then upper plate moves at velocity of 2 meter per second. So I have been given V, it is 2 meter per second. Then the lower plate is stationary. Now they say that the profile is linear. Now if you remember, when I say profile is linear, it means that if I draw the profile, I know the top layer has the velocity V and all the bottom layer has the lower velocity, and if you draw the line, the distribution is a linear line. And we have understood that in the numerical or the derivation aspect that U is equals to V by L into Y. U is equals to V, but this is the distribution of velocity profile. If you are unaware about this, how this came, you can refer to the derivation portion of Newton's law of viscosity. Now see, where U is what? U is the velocity of the fluid layer at a distance of y meters, at a distance of y meters. Now you have been asked the shear stress. You know that shear stress can be determined by Newton's law of viscosity with the formula tau equals to mu du by dy. Yes. Now if I want to know tau at y equals to what? 1 mm. 1 mm distance. So I need to have, see, mu is anyway the fluid property. So fluid property will be same at all the layers. But I need to have du by dy at y equals to 1 mm. So firstly I need to know what is du by dy. But I know that u equals to v by L into y. So I will find the value of du by dy. I know u equals to v divided by L into y. So u equals to what is v? V is 2 meter per second. L is 0.003. So 2 divided by 0.003 into y. This is my u. So now if I differentiate this with respect to y, I will get du by dy is equals to 2 divided by 0.003, which is constant, and differentiation of y with respect to y is just 1. So I will get 2 divided by 0.003. Right? Now in this case, du by dy is a constant term. So what does it mean? It means that du by dy is not changing with respect to y. It is same at all the layers. So which means if I put this value over here, tau at y equals to 1 mm equals to what is value of mu? It is 0.0, I will put the SI unit, right, 0.001 into 2 divided by 0.003. Now if you see, there is nowhere y in this equation. If there would be a y in this equation, you would have find y at 1, I will put the value of y in that equation, right. So which means what? For a linear velocity profile, this is always the case that the shear stress will remain constant for every fluid layer. So many times in the question also, they will not provide you the distance where you need to find shear stress. They will just say find the shear stress in the fluid layer. You need to understand that since the profile is linear, at all the layer fluid stress is going to be same, shear stress is going to be same. Therefore you just find out tau equals to mu du by dy. And remember this, in almost 99% of the cases when you will see numericals, unless and until the profile is given to you, you have to assume this to be the linear profile, right. So let us do the calculation using the calculator. I will get 0.667 Pascal. This is the answer, tau. So tau at this particular layer that we have understood, that is 0.667 Pascal. Let me check the answer. Yes, it is correct. Fine. Let us solve another numerical. I have been given two horizontal plates placed 1.25 centimeter apart. The space between them is filled with the oil of viscosity 14 poises. Calculate the shear stress in oil if the upper plate is moved with a velocity of 2.5 meters per second. Now see, two plates are given to you. The distance between the two plates is 1.25 centimeters. So let us first draw the diagram. So I have been given two plates, the upper plate and the lower plate. The lower plate is fixed, so I will just put it fixed. The upper plate moves with velocity of how much? 2.5 meter per second. And the oil is filled between these plates. The oil is filled. The oil is filled, right? And they said that the distance between the two plates is 1.25 centimeter. 1.25 centimeter. Alright? Now, they are asking to calculate the shear stress. Now, we will see what is data given to us. Given data. I have been given the L first, which is 1.25 centimeter. Again, I am saying that I don't want the values in centimeters. I want this in SI unit, which is meter. So, in centimeter, if I want to convert this to meter, I will divide by 100. If you divide this value by 100, you will shift the point by 2 places. So 0.0125 meters. Then you have been given the viscosity of oil as 14 poises. So which means what? You need to divide, if you want to convert this poise into the Newton second per meter square, or you can say Pascal second SI unit, you will divide always this by a factor of 10. So this is 1.4 poise, 1.4 Pascal second, not poise, right? Pascal second, or you can say Newton second per meter square. Then velocity is given to you, V is as 2.5 meter per second. Now see, as per you have been asked to find the shear stress, question mark. As per the Newton's law of viscosity, tau should be equals to mu du by dy, isn't it? Now, since again there is nothing mentioned about the profile or so always assume that linear velocity profile. So assuming linear velocity profile between the fluid layers, I would say u equals to v divided by L y, isn't it? So therefore du by dy should be equals to what? V divided by L, and which is equals to what is V? V is 2.5. I'll just put it over here, no issues. I'll put the values in this equation. So I'll say tau equals to mu V by L, because du by dy is V by L. So now put the values. Tau equals to what is mu? Mu is 1.4 in SI unit, right? See why we are putting all the value in SI unit, because when you substitute all the values of the variable in SI unit, the value that you will get for the subsequent variable, that is tau, that also will be in SI unit. Okay, so if you put all of them in CGS, you will get this in CGS. So CGS we are not very much acquainted to. So always make sure that you put this value in SI unit. Then V is in 2.5 meter per second. L is 0.0125. Just find out the value of tau. So I'll say it is 1.4 into 2.5 divided by 0.0125. This is 280 newtons per meter square, or you can say Pascal. This is the answer. So they ask you find, now question is at which particular layer is this shear stress? See why they have not mentioned the value of y from where you need to calculate shear stress, because at all the layers the value is going to be same. Why? Because of the linear velocity profile. Since it is linear profile, when you take the derivative will not be a function of y itself. So it will be a constant number. So at any particular y the value is going to be the same. If at all the velocity profile is going to be curvilinear kind of thing, or rather there is a curvature in the profile, second order polynomial, third order polynomial, in that case you will see that if you take du by dy, you will have the variable y in the equation itself. So at that particular time, at each different layer the shear stress is going to be different depending on the value of y. Okay? So we will see that in upcoming numericals also. So I hope you understood this. Thank you so much. We will see you in the next class where we will solve more numericals. Thank you.